Hello there, and welcome to Sleep Science Top 1. Tonight, we drift gently into one of the most exquisite ideas in astronomy, the light year, a measure not of time, but of distance. A journey light travels in 1 year through the vast emptiness of space, a connection linking the vast universe to our quiet corner of reality. As you settle in, let your breathing slow, your thoughts quiet, and allow yourself to drift through the wonder of light itself. If you find peace in these gentle journeys, I invite you to like, subscribe to Sleep Science Top 1, or leave a kind thought below. It helps others discover this tranquil space, one sleepy soul at a time. It assists individuals in uncovering this haven of tranquil education, one drowsy spirit at a time. For the moment, simply allow yourself to rest. Take deep breaths, and let the narrative of light years gently guide you into the night. A light year is a unit of distance that represents how far light travels in 1 year. It is commonly used in astronomy to measure vast distances between celestial objects. A light year does not measure time, even though its name may imply otherwise. It is a span, the journey that light embarks on in a single year as it swiftly navigates the emptiness of space. Light travels at an astonishing speed, racing ahead at nearly 300,000 kilometers per second, surpassing all else in the universe. That amounts to 7 times around Earth's equator in merely 1 second in just 1 year. Light travels nearly 10 trillion kilometers, about 6 trillion miles. The immense expanse we refer to is known as a light year. It serves as the instrument that astronomers employ to gauge the unfathomable distances that separate the stars. When one states that a star is 10 light years away, it signifies that the light observed tonight departed from that star a decade prior, journeying unceasingly through the void to arrive at our sight. Each point of light in the sky holds not only beauty, but also a narrative woven through distance and time. At first glance, the concept appears straightforward. Light journeys, vast distances, over the course of a year. Yet when one takes a moment to reflect on the true significance of this, the meanings reveal themselves gradually, much like the unfolding petals of a celestial bloom. The universe communicates with us, not through the present moment, but through resonances of what has come before. Each upward gaze serves as a portal to the past, revealing the layers of time that have shaped the present. The speed of light remains unchanging. Light consistently moves at a constant speed when traversing through the void of space. This stands as one of the essential truths of our universe, revealed and validated through numerous experiments. Regardless of whether the light originates from a far-off galaxy or a candle held in your hand, it traverses the emptiness at a precise speed of 300,000 kilometers per second. Not roughly, but precisely. This unwavering nature is truly noteworthy. The source of light's movement, whether approaching or receding, holds no significance. The light consistently reaches its destination at an unchanging pace. This peculiar and remarkable truth served as the cornerstone of Einstein's theory of relativity, transforming our comprehension of space, time, and the very essence of reality. The unwavering presence of light emerged as the singular constant in a cosmos where all else was subject to change. Since light maintains a constant speed, it serves as an ideal standard for measurement. With an understanding of the speed of light and the duration of its journey, one can precisely determine the distance it has covered. This is the method by which astronomers gauge the vastness of the universe, not through tangible measures spanning the void, but via the steadfast voyage of photons traversing the shadows. As one gazes upon a star, discovering it to be 100 light-years distant reveals that its light has journeyed toward them for an entire century. The photon embarked on its journey long before your existence, possibly even before the time of your grandparents, traveling silently through the vastness of space until it ultimately arrived at your eye. In that moment, the past and present intertwine as the sunlight journeys for 8 minutes to embrace the Earth. The Sun, the nearest star to us, is located approximately 150 million kilometers from Earth. That appears to be an unfathomable distance, and yet, when viewed through the lens of the cosmos, it is almost within our reach. The sunlight travels for just over 8 minutes to reach us, bringing warmth to our planet. This indicates that as you step outside and experience the warmth of sunlight on your skin, you are actually sensing light that departed from the sun 8 minutes prior. Should the sun abruptly disappear, there would be an 8-minute delay before we would realize its absence. The sky would stay radiant, the warmth would persist, and existence would carry on as if nothing had shifted. It was only after those 8 minutes that darkness would descend. This thought experiment uncovers a deeper significance. The sun is never seen as it exists in the present moment. It is perceived solely as it existed 8 minutes prior. Everything else in the universe reflects this truth, yet the delays continue to extend. The light from the moon, a reflection of the sun's brilliance, takes just over 1 second to reach us. As astronauts traversed the lunar surface, their radio transmissions experienced a peculiar delay, taking a full second to reach Earth, resulting in an unusual rhythm to their conversations. Yet, the moon remains our closest companion. The stars lie in the vastness of space, their distance immeasurable. Even the incredible speed of light appears almost sluggish when confronted with the immense expanse of space. It takes just 8 minutes for light to travel from the sun to Earth, while it takes years to reach us from the nearest stars and millennia to arrive from the farthest galaxies. The vastness of the universe is such that even light, the swiftest entity known, must toil through it like a wanderer on an infinite journey. The closest star to our sun lies more than 4 light-years distant. Proxima Centauri stands as the nearest star to our solar system. Aside from the sun, this diminutive, subtle red dwarf resides a little more than 4 light-years distant. In the vastness of the cosmos, this is almost within arm's reach. However, take a moment to reflect on the true significance of 4 light-years. The light visible from Proxima Centauri this evening embarked on its journey from that star more than 4 years prior. It had been journeying through the vast emptiness of space all that time, hurtling toward us at the speed of light, unceasing and relentless. Should one find a way to traverse the cosmos at light speed, a feat unattainable for any object with mass, the journey to Proxima Centauri, our closest stellar companion, would still span a duration of 4 years. The nearest star system, Alpha Centauri, lies a bit further away at approximately 4.4 light-years. The stars are positioned at such vast distances that no human has witnessed their movement, save for meticulous astronomical observations conducted over many years. Envision the challenge of journeying to Proxima Centauri using the technology available today. The fastest spacecraft, Voyager 1, journeys through space at an impressive speed of approximately 17 kilometers per second. Indeed, it appears swift, especially when measured against human benchmarks. Yet, even traveling at that velocity, the journey to Proxima Centauri would span more than 70,000 years. The journey is completed by light in just over 4 years. This illustrates the significant divide between the speed of light and our own abilities. The stars, appearing so near in the vast night sky, gather in constellations, yet they are separated by such immense distances that light takes years to traverse the space between them. The neighborhood of stars surrounding our sun stretches across dozens of light years in every direction, each one a distant entity, each one impossibly far by any methods we currently have at our disposal. Sirius, known as the brightest star, resides 8.6 light-years from Earth. Sirius shines brightly in the winter skies, a sight that cannot be overlooked. It stands as the most luminous star observable from Earth, eclipsing all others with its radiant blue-white glow. Ancient civilizations observed its ascent and descent, linking their calendars to its rhythms. The Egyptians associated it with the inundation of the Nile. The Greeks linked it to the sweltering heat of summer, leading to the expression dog days. Yet, despite its dazzling brilliance, Sirius is not especially near. It is situated 8.6 light-years distant. The light from Sirius you see tonight left that star more than 8.5 years ago. Had one gazed upon Sirius on the day of their birth, they would have witnessed light that had departed from the star long before their arrival into the world. Each look at Sirius transports one to the past. Sirius shines with remarkable brightness, a result of both its vast distance and its inherent luminosity. It radiates with a brilliance more than 20 times that of our Sun. Should one manage to substitute the Sun with Sirius, the Earth would find itself enveloped in an overwhelming brilliance and warmth, exceeding the limits of what life could possibly withstand. From a distance of 8.6 light-years, Sirius appears as a stunning jewel, illuminating our winter nights with its brilliance, free from any danger. The system consists of two stars that orbit one another in a binary formation. The companion, Sirius B, stands as a white dwarf, a dense remnant of a star that has depleted its fuel and undergone collapse. It completes its orbit around Sirius A every 50 years, remaining unseen by the naked eye, yet unveiled through the lens of telescopes. Two stars, entwined in a celestial dance, their brilliance illuminating the darkness, a journey of nearly 9 years unfolding across the vast expanse of space. Polaris lies about 430 light-years from Earth. For millennia, travelers have been guided by Polaris, the North Star. Positioned nearly directly above Earth's North Pole, it signifies true north in the sky with astonishing accuracy. Throughout history, sailors, explorers, and wanderers have sought guidance from Polaris, relying on its unwavering presence to navigate their journeys. However, Polaris is not nearby. It is situated around 430 light-years distant. This indicates that the light you observe from Polaris this evening departed from that star more than 400 years in the past. As the light embarked on its journey, the year was approximately 1600. During this time, Shakespeare continued to craft his plays. As Galileo embarked on his telescopic observations, a new chapter in the narrative unfolded. The world had transformed in remarkable ways, and yet, the light from Polaris has been journeying toward us all this time, ultimately reaching us tonight to illuminate your view. Polaris is not merely one star. It exists as a complex system of multiple stars. The primary star, Polaris A, stands as a supergiant, its size and brightness far surpassing that of our Sun. Two smaller companions circled around. Using telescopes, astronomers are able to observe and analyze their movements. Yet, to an untrained observer, Polaris stands out as a singular, unwavering point, a guiding light in the northern sky. The star exhibits characteristics of a Cepheid variable, subtly fluctuating in brightness over the course of several days. The pulsations, though subtle and nearly imperceptible without the aid of instruments, imbue Polaris with significant scientific worth. Cepheid variables serve as a tool for measuring cosmic distances, with their pulsation periods uncovering their inherent brightness. Polaris, the steadfast guide star, serves as a celestial benchmark. Betelgeuse may have already met its end. Betelgeuse, the red supergiant that adorns Orion's shoulder, stands out as one of the most iconic stars in the night sky. The warm hue shines brightly amidst the surrounding blue-white stars. Yet, Betelgeuse is not merely vibrant, it is colossal, a dying star expanded to hundreds of times the size of our Sun. If positioned at the heart of our solar system, its surface would reach beyond the orbit of Mars. Betelgeuse is situated around 600 light-years from Earth. This indicates that the light we observe this evening departed from the star approximately in the year 1400 during the medieval period on Earth. As kingdoms rise and fall, explorers embark on their journeys to map the uncharted world. Throughout all that time, light from Betelgeuse has been journeying through the vastness of space towards us. Here lies a thought that stirs discomfort. Betelgeuse approaches the twilight of its existence. Astronomers are aware that it has the potential to explode as a supernova at any moment. In the vastness of the cosmos, the concept of time suggests that events may have already unfolded. The star might have collapsed and exploded centuries past, yet the light from that explosion would still be journeying toward us. The arrival of the light would reveal all that was hidden from view. If Betelgeuse has already gone supernova, we will remain unaware until the light from that event finishes its 600-year journey to us. When it finally arrives, if it ever does, the explosion will be evident, even in the brightness of day. A brilliant new star emerges unexpectedly in Orion. For weeks or months, it will surpass all else, save for the brilliance of the sun and moon, a signal revealing the demise of a star that took place many centuries prior. The Andromeda Galaxy is about 2.5 million light-years from Earth. The Andromeda Galaxy, the closest large galactic neighbor to us, can be seen with the naked eye when the skies are dark. It presents itself as a subtle, indistinct blur, easily missed by those unaware of its significance. Yet that delicate mark holds remarkable value. It is a vast galaxy, home to perhaps 1 trillion stars, situated 2.5 million light-years from our own. Contemplate deeply on the implications of this. The illumination visible from Andromeda this evening embarked on its voyage 2.5 million years in the past. When that light departed from Andromeda, humanity had yet to come into being. The earliest ancestors were on the cusp of diverging from other primates. The planet found itself enveloped in the Pleistocene epoch. Ice ages emerged and receded. Species emerged and disappeared. Throughout that entire duration, light from Andromeda traversed the vast intergalactic void, making its way toward us. The ancient photons that reach your eyes tonight have journeyed through the cosmos for a duration surpassing the existence of human civilization, extending beyond the time Homo sapiens has roamed the Earth. They have traversed an expanse of space so immense that it is fundamentally devoid of substance. In a vast expanse devoid of stars and planets, there lay only an overwhelming emptiness. And yet the light continued its journey, unwavering and constant, at 300,000 kilometers per second, every second, for millions of years. When one gazes upon Andromeda, one is not witnessing it in its current state. One can observe it as it existed during the time when saber-toothed cats roamed the planet. The galaxy that unfolds before you is a relic of ancient history, a glimpse into the depths of time itself. The Andromeda of today, the Andromeda that exists in this very moment, remains a mystery to us. It will remain unseen for another 2.5 million years. Each star scattered across the night sky reveals a glimpse into what once was. This truth resonates with each point of light shining above you. The stars of the Big Dipper, creating that recognizable arrangement, lie at distances between 80 and 120 light-years from Earth. In the early 20th century, their light departed from them. The brilliant star Vega, destined to become Earth's North Star in the distant future, is located 25 light-years away. The light commenced its journey in the late 1990s. Even the planets, appearing near due to their steady and bright shine, reveal to us the echoes of the past. The light from Jupiter travels to us in approximately 40 minutes when the planet is at its nearest point. Saturn's journey extends beyond an hour. When Mars is close, it illuminates our world in mere minutes. Yet, that light remains ancient. What appears before you is not the reality of the present, but a reflection of the past. The night sky does not merely capture a snapshot of the current universe. It forms a tapestry of history, where each star illuminates its unique moment in time. Some stars reveal their brilliance from decades past, while others illuminate the distant centuries. The most distant galaxies observable through advanced telescopes reveal a glimpse into billions of years past, illuminating a period when the universe was still in its infancy. The sky serves as a time machine, apparent to all who gaze upward. This explains why astronomers refer to the act of observing distant objects as looking back in time. They are not expressing themselves in a poetic manner. They are speaking in straightforward terms. Observing an object 10 light-years away reveals it as it existed a decade prior. Observing something 10 billion light-years away reveals the universe as it was 10 billion years ago, a time long before the existence of our Sun or Earth. The vast expanse of light-years unveils the intricate tapestry of the universe's past. The vastness of the universe means that light takes time to traverse the distances, revealing to us various epochs as it reaches our eyes from different points in space. The stars in our vicinity reveal glimpses of the recent past. Far-off galaxies reveal the echoes of a bygone era. Through the careful observation of objects positioned at varying distances, astronomers piece together a narrative that extends back billions of years. The most distant objects ever observed are located more than 13 billion light-years away. Their light has journeyed through the vastness of time, making its way toward us since the dawn of the universe. These galaxies present themselves as they existed in the early days of the cosmos, during the time when the first generations of stars were igniting and the foundations of structure were just beginning to take shape. These are remnants of illumination, preserved communications from the beginning of the universe. Exploring these remote entities uncovers the evolution of galaxies throughout the ages. The early galaxies appeared smaller and more chaotic, characterized by intense star formation. Over billions of years, they intertwined and expanded, establishing themselves within the grand spirals and ellipticals observable in the nearby universe. Through the comparison of galaxies situated at varying distances and consequently across different epochs, astronomers observe the unfolding of evolution. This is the offering of countless years illuminated. Access to history is granted to us. On Earth, the past is examined through fossils, ancient ruins, and written records. In astronomy, the past is revealed to us through the light we observe. The universe holds onto its own past, with photons traveling through the vastness of space, reaching our telescopes as records of times gone by. Each observation unfolds as a journey through time. The observable universe is bounded by the reach of light. The extent of our vision is bound by the speed of light, establishing a clear boundary to what we can perceive. The age of the universe is estimated to be around 13.8 billion years. This indicates that light has been journeying toward us for 13.8 billion years since the moment of the Big Bang. Light from distant sources has yet to arrive, as time has not allowed it to reach us. The extent to which light has journeyed since the beginning of the universe delineates the observable universe. This forms a vast sphere encompassing us, approximately 93 billion light-years across. How can it possibly be larger than 13.8 billion light-years if light has only been traveling for that amount of time? The solution is found within the very expansion of space. As light journeyed toward us, the fabric of space expanded, pushing distant objects even further into the abyss. The observable universe is, in fact, more expansive than one might anticipate. Yet, past this limit, our vision remains obscured, not due to a lack of substance. Indeed, it is assumed that the universe stretches far beyond our observable limits, possibly to infinity. However, the illumination from those areas has yet to arrive at our location. It remains in transit, and may never reach its destination if the universe keeps expanding at a pace that outstrips the speed of light. An entire cosmos lies beyond our horizon, eternally concealed. This boundary transcends mere physical limits. It is merely the boundary of knowledge. Light conveys information, and without its arrival, the information remains absent. A sphere of knowable space envelops us, while everything that lies beyond remains shrouded in the unknown, at least for the time being. The observable universe presents a paradox, both immense and confined, measured in light-years. The journey of light unfolds as it expands. As light journeys through the vastness of space, the very fabric of that space continues to stretch and unfold. This expansion elongates the light, transforming it into longer, redder wavelengths. Astronomers refer to this phenomenon as redshift, marking it as one of the most significant discoveries in the field of cosmology. As light journeys through the vastness of space, it encounters an ever-expanding universe, leading to an increase in its redshift. Through the measurement of redshift, astronomers are able to ascertain the distance of an object. The light, emanating from nearby galaxies, exhibits minimal redshift. The light, emanating from far-off galaxies, exhibits a striking redshift, occasionally stretched to the point where ultraviolet light transforms into visible red or even infrared. The stretching is not solely a result of the movement of galaxies, although galaxies are indeed in motion. The expansion of the universe itself causes this phenomenon, pulling space apart and carrying galaxies along with it. Redshift reveals not only how far away something is, but also how long it has existed. The greater the redshift of a galaxy, the more distant it is, indicating that its light has been traveling for a longer duration, allowing us to observe it further back in time. Redshift transforms into a clock, quantifying the age of the light and uncovering the moment the photons commenced their voyage. A beautiful connection unfolds between distance, time, and the very structure of space. This stretching influences the energy of light as well. Light that has been redshifted carries less energy than it possessed at the moment of its emission. The universe draws energy from photons as they journey through the vastness of expanding space. As ancient light travels from the edge of the observable universe to reach us, it undergoes a transformation, becoming stretched and cooled, arriving faint and weary after its incredibly long journey. There are certain rays of light that will forever remain beyond our grasp. The universe is expanding at an accelerating pace. In the vast expanse of space, distant regions are receding from us at an accelerating pace, propelled by an enigmatic force that astronomers have named dark energy. In the most distant galaxies, the expansion of space occurs at such a rapid pace that the light emitted from them is being swept away quicker than it can journey toward us. This light will remain forever distant from Earth. There exist galaxies whose light embarked on its journey billions of years in the past, hurtling towards us at the speed of light. Yet the vast expanse separating us from them is stretching at a pace that outstrips light itself. The photons advance, yet the finish line continually recedes into the distance. They resemble runners on a treadmill that is set to an overwhelming speed. They are forever out of reach. This light slips away from us, eternally fading into the distant horizon. As time progresses, an increasing number of galaxies will traverse this boundary. In the distant future, billions of years from now, the observable universe will begin to shrink. Galaxies visible to us now will have drifted so far away, propelled by the expansion of the universe, that their light will cease to reach our eyes. In the distant future, should astronomers still roam the cosmos, they will gaze upon a more desolate universe, where the number of galaxies twinkling in their skies has diminished. This represents a significant insight into the nature of light years and the vastness of cosmic distances. The universe holds mysteries beyond our reach. Not all of its light will ever reach us. In distant regions, events unfold, their light traveling toward us, yet destined to remain incomplete in its journey. The universe holds secrets that it will keep to itself, concealed eternally beyond the ever-expanding horizon. The light emanating from the cosmic microwave background represents the most ancient sight we are capable of observing. The ancient light of the universe emanates from the cosmic microwave background, a remnant of the Big Bang's brilliance. This light emerged approximately 380,000 years following the inception of the universe, at a time when it had cooled sufficiently for atoms to coalesce, allowing light to traverse space unimpeded. The light has journeyed ever since, stretched by the expansion into microwaves, and it now fills the entire sky. The cosmic microwave background does not originate from a particular place. It comes from all directions. In the early universe, space itself radiated with a brilliant glow, teeming with hot plasma. As the cosmos expanded and cooled, The once vibrant glow gradually receded into the background radiation that we observe in the present day. By measuring this light, astronomers have uncovered subtle temperature variations that indicate the origins of galaxies, the density fluctuations that ultimately developed into the cosmic structure we observe today. This light has journeyed across the cosmos for more than 13 billion years to arrive at our eyes. It represents the most ancient illumination we can perceive, a communication from the early days of the universe. Prior to this moment, the universe remained shrouded in mystery. The light struggled to move unimpeded, as it was perpetually absorbed and re-emitted by the thick plasma that permeated the vastness of space. The cosmic microwave background signifies the instant when the universe revealed its clarity, heralding the beginning of the era of illumination. Detecting this ancient glow allows one to connect with the very origins of time. Telescopes, adjusted to microwave frequencies, detect photons that have journeyed since the early moments of creation. In every direction, there exists a subtle glow, a consistent presence that echoes the past, a gentle murmur that transcends time. It represents the most distant point we can observe through the use of light. Prior to this moment, only theories and mathematical concepts existed. Neutrinos move at speeds approaching that of light. Light serves as just one of many messengers from the cosmos. Neutrinos, almost devoid of mass, traverse the cosmos, moving at velocities approaching that of light. In contrast to photons, neutrinos exhibit minimal interaction with matter. They traverse whole planets, as if they were mere illusions. Countless particles traverse your body each second, unnoticed and imperceptible, moving forward relentlessly. Neutrinos emerge from the cores of stars, during supernova explosions, and through various other high-energy phenomena. Due to their minimal interaction, they manage to evade areas where light is unable to penetrate. As a massive star meets its end in a spectacular collapse and explosion, neutrinos escape into the cosmos, heralding the impending disaster long before the light arrives. Deep underground, detectors on Earth, shielded from other particles, are capable of capturing these elusive messengers. In 1987, neutrinos from a supernova in the Large Magellanic Cloud were detected on Earth, arriving hours before the light, adding a profound layer of significance to the event. The supernova, known as SN 1987A, captured the attention of many, becoming visible to the naked eye and the subject of extensive study. However, the neutrinos provided earlier validation, journeying 168,000 light-years through the cosmos, evidence that neutrinos convey information similarly to light, provided we possess the tools to detect them. Neutrino astronomy, though still in its early stages, holds the potential to unveil fresh avenues for exploring the universe. Due to their near light speed and ability to traverse matter, neutrinos have the potential to uncover processes that remain concealed from light. Watching the universe unfold through neutrinos resembles experiencing a symphony played on an unconventional instrument. The identical occurrences, the familiar sources, yet a fresh viewpoint emerges, leading to a deeper comprehension. Gravitational waves, too, move at the speed of light. In 2015, humanity made a groundbreaking discovery by detecting gravitational waves for the first time. These phenomena create disturbances in the very essence of space-time, resulting from cataclysmic occurrences such as the collision of black holes or neutron stars. Gravitational waves move at the speed of light, radiating outward from their origin, much like ripples on a pond. Yet, rather than traversing water, they navigate through the very fabric of space, elongating and contracting it as they glide by. Gravitational waves were predicted by Einstein a century ago, yet their faintness means that extraordinary precision is necessary for their detection. The LIGO and Virgo observatories employ laser beams and mirrors, positioned kilometers apart, to detect distortions in space that are smaller than a fraction of a proton's width. As a gravitational wave travels through Earth, it momentarily elongates space in one direction while simultaneously compressing it in another. creating a delicate bending of the very fabric of reality. The waves that were detected in 2015 originated from the collision of two black holes, situated over 1 billion light-years away. The event took place 1 billion years in the past. The gravitational waves, journeying at the speed of light, took 1 billion years to arrive at our doorstep. Upon their arrival, they brought with them knowledge of those black holes, detailing their masses, spins, and the manner in which they spiraled together before ultimately merging. For the first time, humanity experienced the universe in a manner unlike any before. Gravitational wave astronomy unveils a new perspective on the universe. Illumination reveals radiant entities. Neutrinos reveal the intricacies of nuclear processes. Gravitational waves reveal the movement of colossal entities and the distortion of the very fabric of space-time. Each journeys at or near the speed of light, transmitting information across immense expanses. Collectively, they provide a more profound and nuanced insight into the cosmos and its diverse expressions. Fast radio bursts traverse billions of light-years in mere milliseconds. Among the most peculiar signals that astronomers observe are fast radio bursts. These represent powerful bursts of radio waves, fleeting in duration, lasting mere milliseconds. Though fleeting, they unleash energy comparable to what the sun radiates over several days. They emerge unexpectedly in the sky, shining briefly before often disappearing for good. While certain sources have been noted for their repetition, the majority continue to hold an air of mystery. Fast radio bursts originate from distant realms, often billions of light-years away. This indicates that the signals we observe in the present moment were released billions of years in the past. A distant corner of the universe unleashed a sudden, fierce pulse of energy, and that pulse has been journeying toward us ever since. As it arrives, the radio telescopes capture the signal, a brief murmur echoing from the depths of the universe. What leads to these bursts? Astronomers continue their exploration. The prevailing theories suggest the involvement of magnetars, which are neutron stars, characterized by their extraordinarily strong magnetic fields, or the potential collision of neutron stars, along with other, more unconventional possibilities. Every burst transmits information woven into its radio waves, offering insights into the environment it traversed, the distance it covered, and the event that brought it into existence. Fast radio bursts serve as a reminder that the universe teems with phenomena that remain beyond our comprehension. Even after years of gazing at the heavens, fresh enigmas persistently arise. These bursts, journeying across billions of light-years to arrive at our doorstep, serve as messages from the far reaches of the universe, presenting enigmas that beckon to be unraveled. It is evident that light and other electromagnetic waves continue to unveil mysteries, impart knowledge, and astonish us. The Hubble constant measures the rate at which the universe is expanding. Astronomers assess the universe's expansion through the Hubble constant, a term honoring Edwin Hubble, who revealed that far-off galaxies are receding from our vantage point. The Hubble constant reveals the rate at which the universe is expanding. It describes the rate at which a galaxy is moving away in relation to how far it is from us. The more distant a galaxy becomes, the swifter it seems to travel. This connection unfolds through redshift. By measuring its distance, often utilizing Cepheid variable stars or supernovae as standard candles, they determine how far away it is. When one plots velocity against distance, a straight line emerges, illustrating the Hubble law. The gradient of that line represents the Hubble constant. The ongoing debate surrounding the value of the Hubble constant continues to capture attention. Various measurement techniques produce somewhat varying outcomes, presenting a conundrum known as the Hubble tension. However, the idea is evident. The universe expands, and this expansion rate shapes the connection between light-years and time. A galaxy 1 billion light-years away is not merely 1 billion light-years distant in space. It is also moving away from us, propelled by the very expansion of the universe itself. This expansion indicates that the universe was once more compact and will continue to grow in size as time progresses. Rewinding time, we arrive at a point where all matter existed in an incredibly hot, compact form. In that moment, the universe ignites, marking the dawn of space, time, and the very essence of light. The Hubble constant serves as a crucial tool in determining the universe's age and unraveling its historical narrative. Distance and time are inextricably linked by light years. In the realm of daily existence, distance and time exist as distinct entities. One can traverse a specific distance within a designated time frame, yet neither aspect dictates the other. In the vast expanse of the cosmos, light, distance, and time are intricately woven together. A light year serves as both a measurement of distance and a measurement of duration. When one states that an object is 100 light years distant, it implies that the light from that object has journeyed for a century. This bond runs deep. It signifies that as we gaze deeper into the cosmos, we also peer further back into the past. The study of astronomy is deeply rooted in history. Each observation reflects a moment that has already transpired. Objects in proximity reveal glimpses of what has just transpired. Remote entities reveal the history of ages long gone. One cannot observe the current condition of a far-off star or galaxy. They are eternally gazing into the past, limited by the constraints of light's velocity. This implies that the universe possesses layers that extend through both time and space. As the cosmos is mapped, it becomes more than mere locations. It transforms into a tapestry of historical moments. A three-dimensional map of galaxies unfolds as a timeline where distance reflects the passage of time. The universe reveals itself in a magnificent display, each petal representing a distinct era, all laid bare at once as light from various distances converges in harmony. This is the reason light years hold such significance. They serve not merely as practical tools for gauging vast cosmic distances. Rather, they embody the very essence of cosmic time, articulating the narrative of the universe's history. In the absence of light years, conversations about the age of starlight, the evolution of galaxies, and the journey of photons through the vast emptiness would be impossible. Light years provide the language to comprehend our position within a sprawling, timeless universe. Grasping the concept of light years brings a sense of humility. To truly understand the concept of a light year is to experience a profound sense of smallness intertwined with awe. The vast distances at play are so immense that they challenge one's understanding. A single light year measures nearly 10 trillion kilometers. The closest star to our Sun lies more than 4 light years distant. The vast expanse of the galaxy in which we reside spans an impressive 100,000 light years from one end to the other. The observable universe stretches across an astonishing 93 billion light years. They are tiny, fleeting beings on a diminutive planet, revolving around an unremarkable star in a remote section of a galaxy filled with countless other stars, within a universe that holds innumerable galaxies. The light visible tonight has journeyed through unfathomable distances, traversing an expanse so immense that even at the speed of light, it requires years, centuries, or even eons to reach us. And yet, that light finds its way to us. It arrives with unwavering consistency, bearing knowledge, narrating tales, linking us to far-off lands and bygone eras. They are not separate from the cosmos. They are part of it, made of the same matter, governed by the same laws, bathed in the same ancient light. The photons that reach our eyes this evening have journeyed further than any human could ever venture, and yet their voyage concludes here, with us. Grasping the concept of light years reveals not only our smallness in the vast universe, but also the profound ties that bind us to it. They were small, indeed, yet they were also observers, thinkers, beings, capable of measuring the universe and contemplating their place within it. The immense expanse that brings us to our knees also beckons us to marvel, to journey forth, to pursue knowledge. The vastness of light years serves as a navigational tool for that journey, illuminating the grandeur of the cosmos we inhabit. Determining the vast distances of the cosmos requires a clever approach. How do astronomers determine the distances to stars and galaxies? One cannot stretch a tape across the vastness of space. Traveling to distant stars and returning is beyond our reach. Rather, astronomers have crafted a cosmic distance ladder, a sequence of techniques that build upon one another, each extending further than the previous one. At its core lies the speed of light, unwavering and dependable. Radar is employed for detecting nearby objects within our solar system. When radio waves are transmitted to planets or asteroids, they reflect back, allowing us to determine distance by measuring the time it takes for the signals to return. The speed of light is established, leading to the conclusion that time corresponds to distance. Venus, Mars, and the Moon have all been assessed through this method with remarkable accuracy. This provides the initial step on the ladder. For stars that are close to us, parallax is employed. As Earth makes its journey around the Sun, the nearby stars seem to subtly shift in position against the backdrop of the more distant stars. This subtle change, quantified in minute degrees, uncovers the expanse through the lens of geometry. The proximity of a star correlates with the magnitude of its parallax. The Gaia spacecraft has meticulously measured parallax for more than 1 billion stars, creating an extraordinary map of our galactic neighborhood with unparalleled precision. In addition to parallax, astronomers employ standard candles, which are objects with a known intrinsic brightness. Cepheid variable stars exhibit pulsations, with their periods intricately linked to their brightness. Through the measurement of the period and the comparison of the star's apparent brightness with its established intrinsic brightness, one can determine the distance. This approach is effective for stars located millions of light years away, extending its reach into the neighboring galaxies. Supernovae act as beacons in the vastness of the cosmos. For even greater distances, astronomers turn to type Ia supernovae. These are the dramatic explosions of white dwarf stars that have accumulated excessive mass from a companion star, igniting a runaway nuclear reaction. Type Ia supernovae consistently erupt with approximately the same inherent luminosity, rendering them outstanding standard candles. These entities shine with such brilliance that their glow can be perceived across billions of light years. Through the observation of type Ia supernovae in far-off galaxies and the comparison of their apparent brightness with their established intrinsic brightness, astronomers ascertain the distances to those galaxies. This approach unveiled one of the most astonishing findings in the realm of cosmology. During the late 1990s, two independent teams engaged in the study of distant supernovae discovered that the expansion of the universe is accelerating, a phenomenon attributed to dark energy. These supernovae, billions of light years away, revealed that the cosmos is not merely expanding, it is accelerating in its expansion. The light from these explosions, journeying across billions of years to arrive at our eyes, conveyed insights into the universe's condition at the moment they took place. Through the measurement of numerous supernovae across varying distances and times, astronomers were able to outline the history of the universe's expansion. Every supernova serves as a fleeting signal, shining with intense brilliance before gradually dimming into the void. Yet, in that fleeting instant, it casts light upon the immense void, revealing the distance it has traversed, the duration of its journey, and the state of the universe at the time of the explosion. These cosmic lighthouses illuminate the vast expanses of space and time, their light years of journey imparting wisdom to those who seek it. Redshift broadens our perspective, allowing us to glimpse the very limits of the observable universe. For the most distant objects, beyond the reach of standard candles, astronomers depend solely on redshift. Through the measurement of the extent to which a galaxy's light has been stretched, they deduce its distance and the duration of the light's journey. The connection between redshift and distance is clearly defined by the principles of cosmology. Rooted in general relativity, and the observations of the universe's expansion. The most distant galaxies ever observed possess redshifts exceeding 10. Their light has been elongated to such an extent that what was previously ultraviolet or visible light is now perceived as infrared. These galaxies are seen as they existed over 13 billion years ago, shortly after the Big Bang, less than 1 billion years into the universe's history. Their light has journeyed across the vast expanse of time, spanning much of the universe's existence. To observe these distant galaxies, one must utilize powerful infrared telescopes. The James Webb Space Telescope, which made its debut in 2021, was crafted with this objective in mind. The large mirror and sensitive instruments are capable of detecting faint, redshifted light from the earliest galaxies, uncovering the universe's infancy. Every revelation draws us further back in time, inching us toward the origins. Redshift weaves together wavelength, distance, time, and the expansion of space into a cohesive and refined connection. Through the measurement of light's color emanating from a distant galaxy, astronomers uncover not only its location, but also the time it occupies in the vast cosmos. They perceive not merely a place, but a narrative woven through time. Light years transform into chapters of history, inscribed in the ever-changing hues of ancient photons. The cosmic distance ladder is built on light. Every method in the cosmic distance ladder ultimately relies on light. Radar uses radio waves, which are light at long wavelengths. Parallax measures the positions of stars by their light. Standard candles compare the intrinsic and apparent brightness of light. Redshift measures how light has been stretched. Light is the messenger, the courier, carrying information across the void. Without light, we would be blind to the universe beyond our solar system. We would know nothing of stars, galaxies, or the cosmos. Light bridges the gap between us and everything else, traveling faithfully at its constant speed, arriving bearing news from distant realms. The fact that light takes time to travel, that distance and time are linked, is not an obstacle, it is a gift. Because light takes time, we can see the past. Because different distances mean different travel times, we can observe the universe at many different ages. The sky becomes a living museum, displaying the history of creation from the present back to nearly the beginning. Every glance upward is a journey through time, guided by the ancient photons completing their long voyages. Astronomers often speak of looking deep into space, but deep also means back. The two are inseparable. To peer 13 billion light years into space is to peer 13 billion years into the past. The deeper we look, the farther back we see. Light years are the thread connecting here and now to there and then, stitching together a narrative that spans billions of years. Light years show us galaxies in their youth. When we observe galaxies billions of light years away, we are seeing them as they were in their youth. These galaxies are smaller, more chaotic, and filled with intense star formation. They do not yet have the graceful spiral arms or smooth elliptical shapes of nearby mature galaxies. They are still assembling, growing through mergers and collisions, forging the first generations of stars, comparing these young galaxies to older ones nearby. Astronomers trace the evolution of galaxies over cosmic time. They see how structure emerges from chaos, how stars form and die, how galaxies interact and merge, and how the universe transforms from a uniform sea of matter into the rich tapestry of structure we observe today. Light years are the timeline on which this story unfolds. Each light year of distance corresponds to a year of time. Observing a galaxy 10 billion light years away means seeing it as it was 10 billion years ago. By assembling observations of galaxies at many different distances, astronomers create a timeline of galactic evolution. It is like watching a time-lapse video of the universe growing up, from its turbulent youth to its more settled present. This is one of the most profound gifts of light years. They allow us to witness change on timescales far longer than human lifetimes, longer even than the existence of our species. We see the universe not as a static picture, but as a dynamic, evolving system. We watch stars being born, galaxies colliding, clusters forming, and the large-scale structure of the cosmos taking shape. Light from early galaxies reveals the first stars. The first stars in the universe were different from stars today. They formed from pure hydrogen and helium, with no heavier elements. Astronomers call these population 3 stars, and none have been directly observed. They lived fast and died young, exploding as supernovae, and seeding the cosmos with the first carbon, oxygen, and iron. Their deaths made possible the formation of planets and life. Light from these first stars has been traveling for over 13 billion years. The galaxies containing them are so distant and faint that even the most powerful telescopes struggle to detect them. But astronomers are searching. By looking at the most distant, most highly redshifted galaxies, they hope to catch a glimpse of light from the first stellar generation, the stars that lit up the dark universe. When such light is finally detected and studied, it will tell us about the conditions in the early universe. How hot were the first stars? How massive? How quickly did they form? What elements did they create? The answers are encoded in the light, in the spectrum of wavelengths and intensities. Light years of travel preserve that information, delivering it to us intact after its immense journey. Each photon from a first-generation star has crossed nearly the entire observable universe to reach us. It has traveled through expanding space, through intergalactic voids, perhaps through wisps of gas and dust, and finally through Earth's atmosphere to strike our telescopes. In that moment, the photon completes its journey, and we receive a message from the dawn of stars themselves. The universe was once dark, before stars formed. For several 100 million years after the Big Bang, the universe was dark. No stars had yet formed. Space was filled with neutral hydrogen gas, slowly collapsing under its own gravity into clumps that would become the first galaxies. This period is called the Cosmic Dark Ages, a time between the glow of the Big Bang and the ignition of the first stars. Eventually, gravity pulled enough gas together to form the first stars. These massive stars lit up, emitting intense ultraviolet light. This light ionized the hydrogen, turning it from neutral to charged, creating bubbles of ionized gas around each star. As more stars formed, these bubbles grew and merged, eventually ionizing all the hydrogen in the universe. This is called the epoch of reionization. Light from galaxies during reionization has been traveling for over 13 billion years to reach us. By studying these galaxies, astronomers learn when the first stars formed, how quickly they ionized the universe, and what the cosmos looked like during this transformative period. The light carries direct evidence of the transition from darkness to light, from a universe without stars to one filled with them. This ancient light is incredibly faint, red-shifted into the infrared, and requires the most sensitive instruments to detect. But it is there, streaming toward us, across 13 billion light-years of space, carrying news of a time when the universe was just waking up. Light-years measure not just distance, but the great arc of cosmic history, from darkness to dawn, to the brilliant sky we see today. Some photons have been traveling since you were born. Consider this. A photon leaving a star 100 light-years away right now will arrive at Earth in 100 years. If you were born in the year 2000, a photon that left a star 100 light-years away in that same year is arriving right now. It has been traveling your entire life, matching your journey through time as it makes its journey through space. Every moment, new photons are beginning their journeys toward us from countless stars. Some will arrive in years, some in centuries, some in millennia, and every moment, photons that began their journeys long ago are arriving, completing voyages that started before we were born, before human civilization, before humanity itself. The sky is constantly refreshing, a steady rain of ancient light. This means the stars you see tonight are different from the stars anyone has ever seen before. The configuration is the same. The constellations are unchanged, but the specific photons arriving are unique. They are new messengers bearing old news. The light that reaches your eyes tonight is light no one else will ever see. It is yours alone, a personal connection to the cosmos. In a real sense, every glance at the stars is unique. The universe is constantly revealing itself to us, photon by photon, each one completing a journey measured in light years and years of time. We are bathed in light from countless moments in history, all arriving together, overlapping in the present, painting the sky with the past. The Milky Way is 100,000 light-years across. Our home galaxy, the Milky Way, is a vast spiral containing hundreds of billions of stars. From edge to edge, it measures about 100,000 light-years. This means light from stars on the far side of the galaxy takes 100,000 years to reach the other side. The Milky Way is so large that even light, the fastest thing there is, requires 100 millennia to cross it. We live about 2/3 of the way out from the galactic center, in a spiral arm called the Orion Arm. The center of the galaxy lies about 26,000 light-years away. When we look toward the galactic center, we see it as it was 26,000 years ago. Events happening there right now will not be visible to us for another 26,000 years. This is true for every part of the galaxy. Stars in the Milky Way are separated by light years, or tens of light years. The galaxy is not a single place in a single moment. It is a collection of places at different moments, all bound together by gravity, but separated by the time light takes to travel. The Milky Way is spread out in time as well as space. If a supernova exploded on the far side of the galaxy today, we would not see it for 100,000 years. Entire civilizations could rise and fall between the explosion and our observation of it. The galaxy we inhabit is larger than our lifetimes, larger than human history, larger than the history of our species. It is measured in light years, in epochs, in ages beyond our intuition. The galactic center glows 26,000 years ago. When telescopes peer toward the center of the Milky Way, they observe a dense cluster of stars orbiting a supermassive black hole. Astronomers have watched these stars for decades, tracking their orbits, measuring their speeds, and calculating the mass of the black hole. These observations show a black hole of about 4 million solar masses, sitting quietly at the galactic heart. But everything we see there is 26,000 years old. The positions of the stars, the emissions from gas falling toward the black hole, the structure of the surrounding region, all of it reflects the state of the galactic center in the distant past. If something dramatic happened there today, a sudden flare, a star being consumed, we would not know for 26 millennia. This creates a strange disconnect. Astronomers study the galactic center in real time, tracking changes year by year. But the changes they observe are not happening now, they happened long ago. The now at the galactic center is unknowable to us. We can only watch its past unfold. Patient observers separated by light years of distance and years of time. The same is true for any distant object. The current state of a star 10 light years away is unknowable. We see only its past. The star could have exploded yesterday, and we would not know until 10 years from now. The universe's present is hidden from us, fragmented across light years of space. We live in a cosmos where simultaneity is relative, and the present is always out of reach. Andromeda is approaching despite the expansion of space. The Andromeda galaxy, despite being 2.5 million light-years away, is not receding from us like most galaxies. It is approaching while the universe expands and carries distant galaxies away. Andromeda and the Milky Way are bound by gravity, pulling each other closer. They are on a collision course, fated to merge in about 4 billion years. This approach is measurable. By studying the spectrum of light from Andromeda, astronomers detect a blue shift instead of a red shift. The light is compressed, shifted towards shorter wavelengths, because Andromeda is moving toward us at about 110 kilometers per second. In cosmic terms, this is not especially fast, but over billions of years, it adds up. When the collision occurs, it will be slow and majestic. Stars are so far apart that actual collisions between them will be rare, but the gravitational interaction will distort both galaxies, throwing stars into new orbits, triggering bursts of star formation, and eventually merging the two spirals into a single, large elliptical galaxy. Astronomers call the result Milkomeda, or sometimes Milkdromeda. The light we see from Andromeda tonight is 2.5 million years old. The galaxy approaching us is not the Andromeda we observe, but the Andromeda that exists now, unknowable and unseen. We see its past hurtling toward us, a promise of a future collision written in light years and gravity. The cosmos unfolds on timescales that dwarf our own, measured in epochs of light. Light years help us find exoplanets. In recent decades, astronomers have discovered thousands of planets orbiting other stars. These exoplanets are detected through various methods, many of which rely on light. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. This is called a transit, and by measuring the dimming, astronomers can infer the planet's size and orbit. The light we observe during a transit is, of course, not happening now. If a star is 100 light-years away, the transit we see tonight occurred 100 years ago. We are watching the past unfold, observing a planet that crossed in front of its star a century ago. The planet's current position is unknown to us. We see only where it was long ago. This does not diminish the discovery. We are still learning about real planets orbiting real stars, but it reminds us that all astronomy is historical. When we study exoplanets, we study their pasts. When we search for signs of life in their atmospheres by analyzing starlight filtered through alien air, we search for life as it was, not as it is. If we detect biosignatures in the atmosphere of a planet 100 light-years away, we will have found evidence of life that existed a century ago. Whether that life still exists is unknowable. If a civilization on that planet is trying to communicate, their signals will take 100 years to reach us, and our reply will take another 100 years to reach them. Light years separate, not just places, but entire histories. Voyager 1 has barely left the solar system. Voyager 1, launched in 1977, is the most distant human-made object. It has traveled farther from Earth than anything else we have ever built. As of today, it is over 24 billion kilometers away in interstellar space, beyond the influence of the Sun's solar wind. This is an astounding achievement, a testament to human ingenuity and ambition. And yet, in light years, Voyager 1 has traveled only about 0.0025 light-years. Not even 0.25% of a single light-year. Light covers in about 20 hours, what Voyager 1 has taken over 45 years to travel. The spacecraft is moving at 17 kilometers per second, an incredible speed by human standards, but utterly insignificant compared to the speed of light. If Voyager 1 were headed toward Proxima Centauri, the nearest star, it would take over 70,000 years to arrive. The spacecraft would need to cross 4.2 light-years of empty space, and at its current speed, it simply cannot do it in any time frame relevant to human civilization. Light makes the journey in 4 years. Voyager 1 would need millennia. This comparison shows why light years are the only practical measure for cosmic distances. Human spacecraft, even at their fastest, are hopelessly slow compared to light. We cannot travel to the stars in human lifetimes, not with our current technology, but light can. And by studying the light from distant stars, we reach them, in a sense, connecting across light years through photons that make the journey we cannot. Light years reveal the difficulty of interstellar travel. Science fiction often depicts starships traveling between stars in days or weeks. In reality, the distances are so vast that even traveling at a significant fraction of light speed would require decades or centuries. The nearest stars are light years away, and there are no convenient shortcuts. Space is mostly empty, and crossing it takes time. To reach Proxima Centauri in 40 years would require traveling at about 10% of light speed. This is far beyond our current capabilities. The fastest spacecraft we have ever built, the Parker Solar Probe, reaches speeds of about 0.06% of light speed at its closest approach to the Sun. To achieve 10% would require technologies we do not yet possess, enormous amounts of energy, and solutions to countless engineering challenges. And 40 years is just to the nearest star. Most stars are tens, hundreds, or thousands of light years away. To explore the galaxy would require voyages lasting thousands or millions of years, unless we discover new physics that allows faster-than-light travel. The light years separating stars are barriers, vast and daunting, reminding us that the cosmos is not easily conquered. Yet light makes the journey effortlessly. Photons from distant stars reach us constantly, bringing information, beauty, and knowledge. We may never travel to those stars ourselves, but their light travels to us. In this way, we explore the universe without leaving home. Light years are both a measure of what separates us and a measure of what connects us to the wider cosmos. Imagining a journey at light speed, imagine, for a moment, that you could travel at the speed of light. You board a spacecraft, accelerate instantly to 300,000 kilometers per second, and point toward the stars. What would you see? What would you experience? The journey would be unlike anything possible in ordinary life, a voyage through space and time itself. From your perspective, something strange would happen. Time dilation, predicted by Einstein's relativity, would compress your experience of time to zero. At light speed, no time passes for you. Your journey, no matter how many light years it covers, would feel instantaneous. You would arrive at your destination in the same moment you left, experiencing nothing in between. The universe outside would age, but you would not. For observers watching you from Earth, the journey would unfold normally. If you traveled to a star 10 light years away, they would see you depart and then wait 10 years before learning you had arrived, as the news traveled back at light speed. From their perspective, you would age slowly during the trip, time passing more slowly for you than for them, though still passing. But from your perspective, no time would pass at all. This paradox is resolved by relativity. Time is not absolute. It flows differently for observers in different states of motion. At light speed, time stops for the traveler. The light years of distance collapse into nothingness. But this is impossible for anything with mass. Only light itself, massless and eternal, can travel at light speed. For us, made of matter, light speed remains forever out of reach. Nothing, with mass, can reach light speed. The speed of light is a cosmic speed limit, unbreakable by any object with mass. As you accelerate toward light speed, you gain energy. But that energy does not only increase your velocity, it also increases your mass. The faster you go, the heavier you become, and the more energy it takes to accelerate further. Approaching light speed requires infinite energy, which is impossible. This is not a technological limitation. It is a fundamental law of physics. The universe is structured such that light speed is a boundary, a limit that matter cannot cross. Photons reach this speed effortlessly because they have no mass. Electrons, atoms, spacecraft, anything made of matter can only approach light speed asymptotically, getting closer and closer, but never quite arriving. Even reaching 99% of light speed would require staggering amounts of energy. At that speed, relativistic effects become dramatic. Time would slow, distances would contract, and the traveler's mass would increase by a factor of 7. To go faster requires even more energy, and the returns diminish rapidly. Reaching light speed is not a matter of better engines. It is impossible in principle. This is why light years represent such vast distances for material beings. Light crosses them easily, but we cannot. We are bound by our mass, by the structure of space-time itself. The universe allows information to travel at light speed in the form of photons, gravitational waves, and other massless phenomena. But matter must travel more slowly, making the light years between stars formidable obstacles to physical exploration. Time dilation affects travelers at high speed. Even at speeds far below light speed, relativistic effects begin to emerge. If a spacecraft could travel at 50% of light speed, time aboard the ship would pass more slowly than time on Earth. A journey to a star 10 light-years away would take 20 years from Earth's perspective, but only about 17 years for the travelers. The difference is subtle, but real. At 90% of light speed, the effect becomes dramatic. Time aboard the spacecraft would pass less than half as fast as time on Earth. A 20-year journey from Earth's perspective would feel like only about 9 years to the travelers. They would age more slowly, their clocks would tick more slowly, and every process aboard the ship would unfold at a reduced rate compared to the outside universe. This is not an illusion or a trick of perception. It is a real physical effect. Time genuinely passes at different rates for observers in different states of motion. This has been confirmed through countless experiments, from atomic clocks on airplanes to particle accelerators, where subatomic particles live longer than expected because they are moving so fast. Time is flexible, shaped by motion and gravity. For interstellar travelers, this could be advantageous. By traveling at high speeds, they could cross vast distances while aging relatively little. But they would return to find Earth much older than they expected. Light years of distance would translate into decades or centuries of time passing at home. They would be time travelers, moving into the future by traveling through space at relativistic speeds. The twin paradox illustrates time dilation. A famous thought experiment called the twin paradox illustrates these effects. Imagine two twins, one who stays on Earth and one who travels to a distant star and back at relativistic speed. When the traveling twin returns, less time has passed for them than for the twin who stayed home. The traveler is younger, having aged less during the journey. This seems paradoxical because motion is relative. Why is the traveler younger and not the stay-at-home twin? The resolution is that the traveling twin experienced acceleration and deceleration, changing direction to return home. This breaks the symmetry. The traveler moved through space-time along a different path, and that path was shorter in terms of proper time, the time experienced by the traveler. If the twin traveled to a star 10 light-years away, at 90% of light speed, the journey would take about 22 years from Earth's perspective, 11 years out and 11 years back. But the traveling twin would age only about 9 years in total. Returning home, they would find their twin 13 years older. The light years crossed in space, translated into years of difference in time. This is not science fiction. It is a prediction of relativity, confirmed by experiment. Time is not a universal river flowing at the same rate for everyone. It is personal, shaped by motion and gravity. Light years measure not just distance through space, but potential differences in the flow of time. The cosmos is stranger and more wonderful than everyday experience suggests. Communication across light years is slow. Imagine a civilization on a planet orbiting a star 100 light years away. If they send us a message today, a radio signal carrying information across space, that message will take 100 years to arrive. We will not receive it until the year 2125, and if we reply immediately, our response will take another 100 years to reach them, arriving in the year 2225. A simple exchange, a message, and a reply would take 200 years. A conversation would be impossible. By the time we received their message and sent a reply, centuries would have passed. Entire generations would come and go between each exchange. Any dialogue would unfold over durations that surpass human lifetimes, possibly even exceeding the span of civilizations themselves. This represents a significant implication of light years. Civilizations are kept apart from one another. Though the galaxy is filled with intelligent beings, The immense distances render communication painfully sluggish. Radio waves, akin to light, traverse at the speed of light. Information cannot be transmitted at a quicker pace. Each message embarks on a journey across light years, taking years, centuries, or even millennia to reach its destination. This conjures a desolate cosmos, where civilizations exist like isolated islands amid an infinite sea, divided by expanses of space so immense that even their echoes take eons to traverse. Signals are sent into the vastness of space, with the hope that a response might come, yet if a reply does arrive, it may take decades or even centuries for us to understand it. The light years reveal the splendor of the stars, yet they also underscore a profound sense of cosmic solitude. The quest for extraterrestrial intelligence encounters delays measured in light years. The quest for extraterrestrial intelligence, known as SETI, diligently examines the heavens for signals emanating from other civilizations. Radio telescopes attentively seek out patterns that seem unnatural, structures within radio noise that could suggest the presence of intelligent design. Up to this point, there have been no verified signals identified. The universe seems to hold its breath, or so it appears from our perspective. Yet, should SETI achieve success, the consequences become peculiar. Every signal we receive will be a remnant of the past, having journeyed across light years to arrive at our senses. If a signal from a civilization 1,000 light years away is detected, it reveals their existence as it was 1,000 years prior. Their present condition remains a mystery. They might have progressed, they might have stumbled, they might have faded into oblivion. They would be listening to history, and if a reply was sent, it would take another 1,000 years to reach them. When they finally receive our message, 2 millennia will have elapsed since the dispatch of theirs. This is not a dialogue. It represents a sharing of time capsules, messages dispatched into the future with the hope that someone will be present to receive them. The vast distances create a sense of profound disconnection in any interaction. This does not diminish the value of SETI. Uncovering any signal would mark a groundbreaking moment, a testament to our existence alongside others. However, it would not foster any significant dialogue. It would unveil insights, a narrative of the past, a form of archaeology, as one examines the remnants of messages dispatched in a distant time. The light years that allow us to observe distant stars also guarantee that any interaction with extraterrestrial intelligence will unfold slowly, requiring patience and steeped in a rich historical context. To colonize the galaxy would require millions of years. If humanity were to extend its reach beyond Earth, genuinely establishing colonies in other star systems, the journey would take place over epochs that defy comprehension. Even when moving at a significant portion of light speed, the journey to nearby stars would span decades. Building self-sufficient colonies would require more time. Reaching out to more distant stars would take centuries or even millennia. Populating the galaxy would require millions of years. Every colony would exist in isolation, separated by light years from one another. Communication would unfold at a leisurely pace. Journey at an even more leisurely pace. A message dispatched from one colony to another could require decades or even centuries to reach its destination. A traveler journeying between stars may return to discover that the civilization they once knew has transformed into something unrecognizable. The galaxy would remain a fragmented tapestry of human existence. It would be a fragmented collection of autonomous realms. This solitude is dictated by the vastness of light years. Regardless of technological advancements, the speed of light continues to stand as an insurmountable barrier unless new physics introduces the possibility of faster-than-light travel or communication. Light years will forever signify years spent in travel, years marked by communication delays, and years that create a gap between events and their observation. The very fabric of space-time enforces this constraint. Some scientists have pondered the existence of wormholes, imagined tunnels through space-time that might link far-off locations without traversing the intervening space. If such phenomena are indeed possible and can be navigated, they might surpass the light-year limitation, yet they exist solely in the realm of theory. In the vast expanse of the cosmos, light years stand as the authentic gauge of distance, demanding time, patience, and the dedication of countless generations to traverse them. The Fermi paradox raises intriguing questions about the absence of others in the universe. Considering the immense quantity of stars scattered throughout the galaxy, many accompanied by planets that could potentially support life, one might wonder, where is everyone? The inquiry, raised by physicist Enrico Fermi, is known as the Fermi paradox. If intelligent life is prevalent, the galaxy ought to be bustling with civilizations. Some should have emerged millions of years ago. What could be the reason for their failure to colonize the galaxy? What could be the reason for their absence from our sight? One potential explanation relates to light years. The vast distances and lengthy timescales suggest that even a spacefaring civilization could require millions of years to traverse the galaxy. The search for signals has spanned only a few decades. Humanity has achieved the remarkable feat of spaceflight for less than a century. It is possible that they are merely too young, too isolated, and too distant from other civilizations to have made any discoveries about them thus far. Or perhaps the barrier of light years is insurmountable. It is possible that many civilizations may never achieve the capability for interstellar travel. They may be confined to their home systems, with distances that are easily observed yet nearly impossible to traverse, separating them from one another. Perhaps the galaxy is teeming with civilizations, each one isolated, each one gazing outward, each one pondering the reason behind the universe's apparent emptiness. The Fermi paradox presents numerous proposed solutions, yet the immense distances measured in light years play a crucial role in many of these explanations. The vastness of the universe is staggering, with distances so great that even a galaxy teeming with millions of civilizations could feel desolate to each individual within it. Light years stand between us, and not only the stars, but also the neighbors who remain unseen and out of reach. The vastness of light years reveals the universe's predominantly empty nature. As one gazes upon the night sky, it appears to be brimming with stars, yet the vast distances that separate them are truly astonishing. In our region of the galaxy, the average distance separating stars measures approximately 5 light years. Imagine if the sun were reduced to the size of a grain of sand. In that case, the closest star would also be a grain of sand, positioned roughly 5 kilometers away. The void that lies in between is nearly devoid of substance. On larger scales, the void becomes even more pronounced. The vast expanse separating galaxies stretches across millions of light years. Amidst the vast expanse of galaxy clusters, the voids stretch across hundreds of millions of light years. These voids hold nearly emptiness. There were no stars, no galaxies, only a sparse scattering of stray atoms in each cubic meter. The universe presents itself as an expanse of emptiness, where matter is clustered into small pockets, isolated by immense voids. The vastness of this emptiness is measured in light years. It reveals to us that the universe is not a bustling expanse. It is vast in a way that defies understanding. The vastness of space is filled primarily with a subtle echo of matter and the lingering background radiation that remains from the Big Bang. The stars, planets, and galaxies, along with all the structures we observe, represent merely a small portion of the vast expanse of the universe. This emptiness is not a flaw, it is an essential quality. The universe's expansion has dispersed matter, resulting in the immense distances that are measured in light years. The vast distances enable light to traverse the expanse, conveying information throughout the universe. They also forge the silence and isolation that define existence on cosmic scales. They are islands in an ocean of space, separated by light years from any other shore. The notion of the present moment loses significance when viewed from the vastness of the cosmos. On Earth, a shared present unfolds for all. When an event occurs in one location, news of it can reach another location almost immediately, or at least within seconds, thanks to advancements in communication technology. The notion of now appears straightforward, yet when viewed through the lens of the cosmos, it becomes devoid of significance. The speed of light is limited, and the transmission of information requires time. There exists no singular present moment that is shared by all. Imagine two events occurring simultaneously, one taking place on Earth and the other on a distant star 10 light-years away, both aligned with our current timekeeping. From an external viewpoint, they occur at the same time. However, an observer traveling at high speed toward that star would perceive the event occurring on the star as happening first. An observer distancing themselves from that star would perceive it as occurring in the present moment. Simultaneity exists as a relative concept rather than an absolute one. This indicates that there is no definitive answer to the inquiry regarding the current events unfolding in Andromeda. From our perspective, an event is currently unfolding in Andromeda that will reach our eyes in 2.5 million years. However, when viewed from an alternate perspective, a different conclusion would be accurate. The idea that there exists a universal present moment where everything unfolds simultaneously is merely a construct shaped by our constrained viewpoint. The vastness of light years underscores the relativity of simultaneity. Due to the nature of light's travel and the relativity of time, defining a cosmic now becomes an impossible task. The universe lacks a singular present moment that is universally experienced by all observers. Countless present moments exist, each unique to the observer, shaped by their motion and position. The sole common experience lies in the past, in the events whose illumination has already reached us. The observable universe possesses boundaries shaped by light. The observable universe represents only a portion of the entire universe. This is the segment of the universe that has allowed light to travel to us since the moment of the Big Bang. A sphere forms around us, with Earth positioned at its center, spanning approximately 93 billion light-years in diameter. Beyond this boundary, light remains unseen, still waiting to touch our world. The unseen remains elusive, forever beyond our grasp, as the relentless acceleration of space's expansion persists. This boundary perpetually extends, as light from ever more remote areas has the opportunity to reach us. However, due to the expansion of space itself, certain areas are receding at a pace that exceeds the speed of light. These regions will remain forever hidden from our view. The observable universe expands, while, paradoxically, it also contracts as remote galaxies speed away beyond the visible boundary. The boundary of the observable universe signifies a threshold of understanding. One cannot perceive what lies beyond, not due to an absence of existence, but rather because the illumination has yet to arrive. It represents a horizon, not as a limit in space, but as a threshold in time. They find themselves encompassed by this horizon at every turn, delineating what can be understood and what remains eternally concealed. The horizon is defined by light years. The observable universe spans roughly 13.8 billion light-years in radius, measured by the time light has traveled. However, due to the expansion of space throughout the journey, the true distance to the edge has increased, now estimated at approximately 46.5 billion light-years. This represents the utmost distance we can perceive through the use of light. It stands as the definitive gauge of our celestial surroundings. The expansion, driven by dark energy, surpasses the speed of light. During the late 1990s, it was revealed by astronomers that the expansion of the universe is accelerating. A mysterious force known as dark energy is accelerating the expansion of space at an increasing rate. This acceleration signifies that distant galaxies are moving away from us at increasingly rapid velocities. The most distant galaxies are already retreating at speeds surpassing that of light, propelled by the very expansion of space. This does not contravene the principles of relativity. While nothing traverses the cosmos quicker than light, the very fabric of space can stretch at any speed. Galaxies nestled within that vast expanse are swept along, and the gap separating us from them can expand at a pace surpassing that of light itself. This indicates that light from the farthest galaxies is engaged in a futile struggle, attempting to reach us through a space that is expanding at a pace quicker than the speed of light itself. Some of this light will eventually find its way to us, but only the light that is already within reach. Light from galaxies that lie beyond a certain distance will remain forever out of our reach, regardless of how much time passes. The expansion will perpetually draw them away more swiftly than light can ever reach. These galaxies exist beyond the cosmic horizon, eternally out of reach, their light forever lost to humanity. Mysterious dark energy, in its enigmatic essence, is altering the trajectory of light years ahead. With the passage of time, an increasing number of galaxies will venture beyond the horizon. The observable universe is destined to hold a dwindling number of galaxies as they speed away, slipping beyond our grasp. In the distant future, observers within our galaxy will witness a universe transformed into a more solitary expanse, where only the nearest clusters of galaxies will still be discernible. The light years that once linked us to far-off galaxies will have transformed into insurmountable chasms. Future astronomers might observe a sky that is shrouded in darkness. Envision a time when astronomers, eons from now, gaze into the cosmos, long after the sun has met its end. From the remnants of our galaxy, or its union with Andromeda, observers will gaze out to find a diminished number of galaxies. Many will have sped past the horizon, their brilliance no longer visible to the onlooker. The cosmic microwave background will have shifted to a point of being undetectable. Should these future observers come into being, they may not uncover the origins of the Big Bang. They may be unaware that the universe had a starting point, or that it continues to expand. The evidence, traversing the vast expanse of light years, will have diminished to the point of being undetectable. One might assume that the universe remains unchanged and everlasting, merely housing the local group of galaxies amidst an expanse of darkness. This thought lingers persistently. It implies that the present time holds a unique significance. In an era where the remnants of the Big Bang remain evident, distant galaxies continue to be observed, and the universe's history can still be deciphered from the light that travels to us. Future civilizations might not encounter this chance. The light years that presently convey information will ultimately cease to span the expanding distances. It also implies that there could be elements of the universe beyond our observation, as we exist in a time that is too far removed. It is possible that earlier times held proof that has since vanished from our view. It is possible that the universe holds within it structures or events that occurred eons ago and in distant realms, their light forever beyond our reach. Much is observed, yet not all is revealed. The observable universe serves as a portal, yet that portal is gradually shutting. Light is bent across light years by gravitational lensing. Light is bent by gravity. Enormous entities such as galaxy clusters distort the very fabric of space-time, causing light that traverses this altered realm to take on curved trajectories. This phenomenon, anticipated by Einstein and validated through observation, is known as gravitational lensing. It enables astronomers to observe objects that might otherwise remain concealed or too dim to notice. When a massive galaxy cluster stands between us and a more distant galaxy, the gravity of the cluster bends the light from the distant galaxy, magnifying and distorting it. At times, several images of the same galaxy emerge, elongated into arcs or rings. This phenomenon uncovers galaxies that are billions of light years distant, which would remain unseen without it. The light emitted by these galaxies has journeyed across the cosmos for billions of years, shaped and directed by the gravitational influence of intervening mass. Time delays are also created by gravitational lensing. The light, traversing various routes around an object, reaches its destination at distinct moments. In the vastness of the cosmos, should a distant galaxy experience a variable event, such as a supernova, observers may witness it multiple times, with each glimpse revealing the spectacle at a slightly different moment in time. The light journeyed across the same expanse in light years, yet it navigated varied paths through the bends of space-time, ultimately reaching its destination at different moments. The bending of light across light years unveils the distribution of mass throughout the universe. Astronomers map the invisible dark matter that fills galaxy clusters by studying how light is lensed. They measure the cosmos, mapping the unseen gravitational pull of matter that eludes direct observation. Gentle, enduring, and unwavering, light carries knowledge not only from its source, but from everything it has passed along its vast journey. The horizon of the observable universe surrounds every observer. Each observer in the universe finds themselves enveloped by their own light horizon, marking the limits of their perception. For them, that boundary lies approximately 46.5 billion light-years distant in all directions. Yet, a watcher from a far-off galaxy perceives a distinct horizon, uniquely focused on their own position. Segments of our observable universe lie beyond their horizon, while portions of theirs extend beyond ours. This implies that various observers perceive distinct segments of the universe. There is certainly some overlap. The observable universe is shared with nearby galaxies. Yet, galaxies that are billions of light-years apart, located on opposite ends of our observable universe, remain oblivious to one another. The illumination from one has yet to arrive at the other. They exist in a realm of mutual invisibility, divided by distances so immense that even light cannot traverse them in the expanse of the universe's age. This results in an unusual circumstance. The vastness of the universe likely extends far beyond the reach of any observer's gaze. It could possibly extend beyond all limits. Yet, every observer finds themselves confined within their own sphere of illumination, a realm of clarity that envelops them. Outside that bubble, the universe unfolds, yet remains a mystery. In different regions, across various galaxies, and within diverse structures, existence unfolds. Yet, they remain beyond our observation, as the light will forever elude our reach. The light horizon does not serve as a tangible boundary. The finite speed of light and the limited age of the universe lead to this consequence. The distance light has traveled is limited by the time elapsed since the Big Bang. This establishes an inherent constraint on understanding, a threshold past which knowledge remains inaccessible. In a certain way, they find themselves confined within their own light cone, only able to witness the past of areas from which light has traveled to them. Each photon holds a narrative of its own. Upon reaching your eye or telescope, a photon has traversed a remarkable journey. The journey could have spanned years, centuries, or even billions of years. Throughout its journey, the photon traversed an expanding universe, moving through areas of varying density, possibly navigating gas clouds or circumventing gravitational lenses. Every segment of the journey etched delicate impressions upon the photon. The wavelength of the photon reveals insights into its origin and the path it has traveled. When it has been redshifted, it is evident that it originated from a distant place, traversing the vastness of expanding space. Should it appear blue or ultraviolet, it is clear that it originated from a hot source. When its spectrum displays absorption lines, it indicates that it has traversed gas that absorbed certain wavelengths, thereby uncovering the composition of that gas. Each photon serves as a repository of information. Through meticulous examination of photons, astronomers unveil not only the origin, but also the path taken. They discover the density of gas that exists between us and far-off galaxies, the arrangement of matter, the pace of expansion, and the circumstances that prevailed in the early universe. Light transcends mere signaling. It is a historian, bearing the knowledge of all it has encountered throughout its vast journeys across the cosmos. This is the reason astronomers refer to photons as messengers. Every individual carries tales from far-off lands and bygone eras. Every tale unfolds, revealing its essence to those who can decipher it. The light years they have traversed hold significance beyond mere emptiness of space. Subtle influences abound, shaping the light, encoding information, and enabling a deeper understanding of the universe that the photons have traversed. Light possesses the ability to be stored and delayed. Within the confines of laboratories, researchers have discovered methods to decelerate light, ensnaring it within meticulously crafted substances. The movement of light through these materials is significantly slower than its pace in a vacuum, at times reduced to a mere walking speed, or even brought to a complete standstill. This does not breach the essential speed limit. Light in a vacuum consistently travels at light speed. However, its pace can be diminished when it passes through matter. This deceleration happens as atoms in the material absorb and then re-emit photons. The photons continue their journey at light speed between atoms, yet the cycle of absorption and emission slows their advancement. The outcome reveals a speed that is notably less than that of light. In extreme cases, light can be completely halted, preserved in atomic states, and subsequently released at a later time. These experiments do not contribute to understanding astronomical light years. While we cannot slow down light from distant stars, it unveils the remarkable adaptability of light's behavior and the intricate interactions between matter and energy. It is also shown that the speed of light, regarded as a universal limit, pertains specifically to light traveling in a vacuum. In various situations, light can exhibit unexpected behaviors, influenced by the characteristics of the medium it traverses. For astronomical purposes, light journeys freely through the immense voids that separate stars and galaxies. The vast emptiness of space enables photons to travel at their constant speed for billions of years, journeying across light years without any deceleration. This explains the feasibility of astronomical observations. If space were filled with a substance that impeded light, the photons would either fail to reach us entirely or arrive so delayed and scattered that they would offer us no knowledge. Cosmic rays, while not light, traverse the cosmos at speeds that approach that of light itself. As light traverses the vast expanse of the universe, cosmic rays also journey through, consisting of high-energy particles such as protons and atomic nuclei, propelled to nearly the speed of light by cataclysmic events. These particles journey across the vastness of space for light years, occasionally colliding with Earth's atmosphere and resulting in showers of secondary particles. They may not be light, yet they serve as messengers of a unique nature. Cosmic rays convey insights regarding their origins. The most energetic ones originate from beyond our galaxy, potentially arising from supermassive black holes or the collision of galaxies. Their energies are remarkable, surpassing anything that can be attained in human-engineered particle accelerators. Examining them uncovers phenomena that elude our ability to reproduce on Earth, showcasing intense physics taking place in the most tumultuous regions of the universe. However, cosmic rays encounter an issue that light does not face. Charged particles exist, and these particles experience deflection when subjected to magnetic fields. As they journey through the vastness of space, navigating the intricate magnetic fields of the galaxy, their trajectories curve and spiral in unexpected ways. As they arrive on Earth, their trajectory has shifted away from their origin. They come from every direction, their beginnings intertwined. Light, devoid of charge, moves in direct paths and is less influenced by the curvature of gravity. This transforms it into a significantly more effective communicator for astronomy. A photon can be traced back to its source, revealing its origin. Cosmic rays, while moving at nearly the speed of light and possessing immense energy, remain a mystery in terms of their origins. Anonymous messengers traverse the cosmos, their histories obscured by the magnetic fields encountered over vast distances of light years. The velocity of light represents the pace of causation. The speed of light transcends mere travel. It embodies the rate at which cause and effect unfold throughout the cosmos. No force can affect another as swiftly as the speed of light. Should an event take place in this location, its impact cannot extend to another area until the time it takes for light to journey there has elapsed. This represents the pace of causality, the utmost velocity at which information and influence disseminate. This suggests that there exists an essential framework governing the occurrences within the universe. If two events are distanced by more light years than the time permits for light to traverse, they are unable to affect one another. They exist in a state of casual disconnection, intertwined in each other's future or past, yet absent from one another's present. The light cone, representing the area accessible to light, delineates the relationships between various events and their potential influences on one another. On Earth, this structure remains unseen, as light traverses planetary distances with remarkable speed. Yet, on a cosmic scale, it influences all that exists. The universe exists not as a singular moment, but as a tapestry of causally linked areas, each capable of affecting only that which is illuminated by light. Beyond that, events exist in their own realms, unfolding in isolation, separated by the vast light years that hinder any form of communication. This illustrates the revolutionary potential of faster-than-light travel or communication. Such an occurrence would disrupt the natural order, permitting effects to manifest prior to their causes, leading to paradoxes and contradictions. It is widely held among physicists that this notion is unattainable, as the very fabric of space-time seems to prohibit it. Light years transcend mere distances to be traversed. These elements are essential aspects of the universe's organization, the connections between events, and the very structure of reality itself. Relativity intertwines space and time, illuminated by the essence of light. The foundation of Einstein's theory of relativity is built upon the unchanging nature of light speed. The speed of light remains constant in a vacuum, unaffected by the movement of either the source or the observer. This straightforward truth, validated through experimentation, sparked a transformation in the field of physics. Space and time, once considered distinct, were unveiled as facets of a unified whole, known as space-time. In the realm of space-time, distances are quantified not solely by spatial measurements, but also by temporal ones. This is captured perfectly by light years. A light year represents a distance in space, defined by the distance that light travels over the span of a year. The relationship between space and time shifts with the speed of light. Traversing through space resembles the passage through time, with both elements intertwined within a four-dimensional framework. This unification reveals the reasons behind the varying experiences of time for observers in distinct states of motion. They traverse the vast expanse of space-time, each on their own distinct journey. A traveler moving at high speed navigates a distinct path through space-time compared to someone who remains at rest, and this path entails a reduced passage of proper time. The distances they traverse in the cosmos reflect the variations in the time they perceive. Relativity provides insight into the reasons behind the limitation of light speed. To move faster than light would resemble a journey into the past, disrupting the very fabric of cause and effect. The framework of space-time does not allow for it. The essence of light speed is intricately interlaced within the very fabric of reality, serving as a fundamental constant that influences all aspects of existence. Light years hold significant meaning. These represent the very fabric of space-time, with distances articulated through the singular speed that remains constant and universal. The universe commenced as a singular point, even smaller than a light year. 13.8 billion years in the past, the universe came into existence. Initially, everything that would later evolve into the expansive universe, space, matter, and energy, was confined to a space tinier than an atom. In a time before light years existed, the universe was a blank canvas, waiting to be filled with stories yet untold. In its infancy, space was a minuscule, compact entity, radiating heat that surpassed all comprehension. In those initial moments, the universe surged forth, surpassing the speed of light. This is permitted as the very fabric of space can stretch at any pace. Motion through space cannot exceed the speed of light. Yet, space possesses the ability to expand, elongate, and transport matter at any speed. In an instant, the universe expanded from a size smaller than a proton to one larger than a galaxy. This phenomenon is referred to as cosmic inflation. As inflation came to a close, the universe persisted in its expansion, albeit at a more measured pace. Light was now able to traverse the vastness of space without hindrance. Yet for the initial few 100,000 years, the cosmos remained shrouded in opacity, a swirling mass of plasma that scattered the photons in every direction. It was only after the universe had cooled and atoms had taken shape that light commenced its journey across the vastness of space. The initial light years emerged as distances expanded and photons embarked on their travels. From that small origin, the cosmos has grown to its vastness today. The observable universe extends across a vast expanse of 93 billion light-years. The vast expanses that separate galaxies stretch across millions or even billions of light-years. The vastness is unfathomable when contrasted with the singular point in space where everything originated. And yet, every light-year of space, every photon traversing it, connects back to that moment, that minuscule beginning. The light from the Big Bang envelops everything around us. The cosmic microwave background, a subtle radiance remaining from the Big Bang, can be observed in all directions. It originates from the instant when the universe revealed its clarity, roughly 380,000 years following the inception. During that period, the universe measured approximately 1,000th of its present dimensions. The light that was released has been journeying ever since, transformed by the expansion into microwaves. This light has journeyed across the cosmos for more than 13 billion years. It has journeyed across the vast expanse of the observable universe to arrive at our doorstep. In the act of detecting the cosmic microwave background, one finds oneself gazing upon the most remote light imaginable, the very boundary of the observable universe. The universe is revealed in its early stages, radiating a consistent glow in all directions. The cosmic microwave background envelops us like a sphere, yet it is not a sphere located in space. It exists as a sphere within the fabric of space-time, marking the limits of what can be observed in the universe. Each point on that sphere maintains an equal distance in terms of light travel time, approximately 13.8 billion light-years. However, due to the expansion of space, the true distance is significantly larger, approximately 46.5 billion light-years. This timeless illumination links us to the dawn of existence. It is a message from the dawn of the universe, traversing light-years and eons to reach our telescopes in the present day. Through the examination of minute temperature variations, astronomers chart the early universe, uncovering the origins of galaxies and the density fluctuations that evolved into the vast structures we observe today. The cosmic microwave background represents an extraordinary journey through light years, encompassing almost the entirety of the universe's existence. Supernovae unveil the universe's accelerating expansion. In the late 1990s, two teams of astronomers embarked on a quest to study distant Type Ia supernovae, employing these celestial phenomena as standard candles to gauge the vastness of cosmic distances. They anticipated discovering that the expansion of the universe was diminishing, held back by the collective gravity of all the matter contained within it. Instead, they uncovered something astonishing. The expansion was picking up speed. Far-off supernovae, located billions of light-years from Earth, emerged less luminous than anticipated. This indicated that they were more distant than expected, as if the universe were merely drifting along. The expansion of space was now occurring at a pace greater than it had been when that light was first emitted billions of years prior. There was a force at work, driving the universe to stretch further and faster, defying the pull of gravity. This revelation uncovered a shadowy energy, an enigmatic force or characteristic of the cosmos that propels the acceleration forward. Dark energy makes up about 70% of the universe's total energy. We do not know what it is, only that it exists, and that it is causing the universe to expand faster and faster. The distance between galaxies is expanding at an ever-increasing pace. The supernovae that revealed this are billions of light years away. Their light journeyed across the vastness of time, bearing tales of the universe as it once was. Through the observation of supernovae across varying distances and times, astronomers mapped the universe's expansion history, uncovering that the acceleration commenced approximately 5 billion years ago. Light from across light years of space rewrote our understanding of the cosmos. The fate of the universe depends on dark energy. If dark energy continues to dominate, the universe will expand forever, accelerating without end. Galaxies will move farther and farther apart. Eventually, all galaxies outside our local group will recede beyond the horizon, their light unable to reach us. The universe will become darker, lonelier, colder. Stars will exhaust their fuel, black holes will evaporate, and in the unimaginably distant future, space itself may be all that remains. This scenario is called the Big Freeze, or heat death. The universe does not end in a dramatic collapse, but fades away into cold, dark, empty space. Light years will continue to grow, distances increasing without limit, until the universe is so diffuse that nothing remains but empty space stretched across incomprehensible distances. Alternatively, dark energy could change. If it weakens, gravity might eventually halt the expansion and pull everything back together in a big crunch, the opposite of the Big Bang. If dark energy strengthens, it could tear galaxies, stars, and eventually atoms apart in a big rip. These are speculative, but the point is clear. The future of the universe depends on how dark energy behaves, and light years are the measure of that future. For now, observations suggest a big freeze. The universe will expand forever, and the light years separating galaxies will grow without bound. Future observers, if any exist, will see fewer and fewer galaxies until only the local cluster remains. The light from distant galaxies traveling across light years of space will fade into the void, stretched beyond detection by the relentless expansion. Our view of the universe is constantly updating. Every moment, new photons arrive from across the universe, bringing fresh information. The sky is not static. It is constantly refreshing. A stream of light carrying news from different distances and different times. Nearby stars show us the recent past. Distant galaxies show us the ancient past. Together, they paint a picture of the universe as it was across time. Astronomers take advantage of this by observing, over time, variable stars change brightness. Supernovae flare and fade. Galaxies collide and merge. By watching the sky for years or decades, astronomers see these changes unfold. But remember, the changes they see are not happening now. They happened long ago, and the light is only just arriving. This continuous update means our knowledge of the universe is always improving. New light arrives, carrying information about events we have not seen before. Telescopes scan the sky, cataloging objects, measuring distances, and studying light from across the light years. Each observation adds to our understanding, building a more complete picture of the cosmos. The sky you see tonight is different from the sky anyone has ever seen, not in arrangement, but in the specific photons arriving. The light reaching your eyes is unique, a moment in the endless stream of photons crossing space. Tomorrow night, new photons will arrive, continuing the story. The universe reveals itself slowly, one light year at a time, one photon at a time. Light years are a bridge between the human and the cosmic. We measure our lives in years, decades, if we are fortunate. A century is a long human lifespan, but light years stretch far beyond human scales. A single light year is longer than recorded history, longer than civilization, longer than humanity has existed as a species. Light years are the realm of stars, of galaxies, of the cosmos itself, and yet we understand them. We can imagine them, calculate them, observe their effects. Through science and mathematics, through the patient accumulation of knowledge, humans have reached beyond our brief lives to grasp the immensity of the universe. Light years are both utterly alien to human experience and deeply familiar, a concept we have made our own. This is the power of understanding. We cannot travel light years. We cannot live long enough to see a photon complete its journey from a distant star. But we can comprehend what a light year means. We can trace the path of light across the cosmos, understand the time it takes, and use that understanding to explore the universe. Light years bridge the gap between our smallness and the vastness around us. When you look at a star and know it is 10 light years away, you are connecting your brief existence to a journey 10 years long, to a star that may be billions of years old, to a photon that has traveled farther than you will ever go. In that moment, you touch the infinite. Light years are not just measurements. They are invitations to wonder, to imagine, to understand our place in a universe far grander than ourselves. Conclusion. Light years illuminate our place in the cosmos. Light years are more than units of distance. They are the language of the universe, the way we speak about the immense scales of space and time that define existence beyond Earth. Every light year represents a year of light's journey, a connection between distant places and different times, a thread in the vast tapestry of the cosmos. When you see a star, you are seeing its past. The photon that reaches your eye has traveled across light years of empty space, carrying information about a sun that may have changed or died since the light began its journey. You are a witness to history, an observer of events long past, connected across the void by the patient stream of light. The universe is vast. The distances are incomprehensible. The timescales stretch beyond imagination, but light crosses those distances faithfully, bringing us knowledge, beauty, and connection. Through light years, we learn about the birth of stars, the death of galaxies, the expansion of space, and the history of everything. We see not just where things are, but when they were. As you lie here, breathing slowly, drifting towards sleep, imagine the photons that have crossed light years to reach you tonight. Imagine the stars whose light left them when your grandparents were young, when the Romans built their empire, when dinosaurs walked the earth. Imagine the galaxies whose light has been traveling for millions or billions of years, light from a universe younger and stranger than the one we know. Light years connect us to all of it. They show us that we are part of something unimaginably vast, ancient, and beautiful. We are made of atoms, forged in stars, bathed in light that has traveled across the cosmos, living on a small world in a quiet corner of an ordinary galaxy among billions. We are both insignificant and precious, tiny and connected, brief and part of something eternal. The light that surrounds us has always been there, streaming across space, waiting to be seen. The stars have always been shining, their photons beginning journeys that may last years or centuries before finding an eye to witness them. And we, for this brief moment, are here to see them, to understand them, to marvel at the light years they have crossed. Let the calm of this understanding wash over you. Let the vastness become not frightening, but peaceful. You are held by the same laws that govern the stars, made of the same matter, seeing the same ancient light. You are part of the universe, and the universe is part of you. The light years that separate you from distant suns also connect you to them, binding everything together in a web of light and time. As you close your eyes, picture the night sky above. See the stars scattered like diamonds against the dark, each one a distant sun, each one separated from you by light years of space and years of time. See the Milky Way arching overhead, a band of light from billions of stars within our own galaxy. See the faint smudge of Andromeda, an entire galaxy visible to the naked eye, 2.5 million light-years away. Know that the light you imagine seeing has traveled all those years to reach this moment. Know that new photons are always arriving, always completing their journeys, always bringing news from the cosmos. Know that you are witnessing the universe as it unfolds across time, layer by layer, light year by light year, revealing its history in the glow of stars. Let this knowledge bring you peace. Let it quiet your thoughts. May it serve as a reminder of your role within a grander scheme, a magnificent expanse that spans light years and eons, yet is present in this moment, observable by all who gaze upward and ponder. The universe communicates through the language of light, with light years serving as the words that convey its narrative. Inhale slowly. Take a moment to unwind. As you drift into sleep, feel the gentle understanding that you are part of a cosmos vast beyond imagination, present in every beam of starlight, every photon crossing space, and every light year connecting the distant past to the present moment. Sleep well, take care, and get some good rest. And may your dreams be illuminated by the gentle radiance of stars whose light has journeyed across vast distances to find you. And so, we come to the gentle close of our journey tonight. Light years are more than numbers. They are bridges of time, connecting us to the ancient past and the infinite future of the cosmos. Every star you see is a reminder. The universe is sharing its history with you, one photon at a time. Thank you for drifting with Sleep Science, Top 1. If this peaceful exploration brought you calm and wonder, please like the video, subscribe for more soothing science stories, and share one thought below. What surprised you most about light years? Your support helps us reach more sleepy souls, seeking knowledge wrapped in stillness. Breathe deeply, let go, and drift into dreams illuminated by starlight that has traveled billions of years just to find you. Sleep well, dream deeply. Good night.